Thanks for having me, guys. So basically, I'm just here to talk about a project that I worked on. Did some research for something called a Bitcoin Honeypot. So it's basically leaving a wallet on the floor of the internet and seeing what we can find. So a bit about me. So I run a consultancy called FortSafe. I'm the director of cybersecurity there. I've got about 20 years experience in IT security, in the IT industry. I've got an engineering degree in networks and a master's in IT security. I've got experience in the utilities, government and financial sector for cybersecurity consulting, including penetration testing, incident response, secure software development lifecycle, and governance, risk and compliance. So the agenda today is, can we trap hackers looking for the free Bitcoin? So the first, I'm going to cover the development of a honeypot for a Bitcoin full node, deployment of a honeypot, and catching a hacker trying to steal from the honeypot. And that's where we get the cool stuff. So a bit of background on Bitcoin. Bitcoin is a cryptocurrency running using a blockchain. And it's the nodes are on a peer-to-peer network, and it's basically a distributed ledger. So you have a block which has a list of transactions, transferring money from value from one address to another, and then each of those transactions gets a hash, and then from those hashes you hash those to get the root of a Merkle tree, and with that Merkle tree root hash, you also get the hash of the previous block, and you put those together, and that becomes a hash for the entry into the second block. And likewise, you have the transaction IDs, Merkle root tree, etc., etc. So the blockchain consists of blocks with the header, Merkle tree, and data located in the transactions in the current block. So transactions look like this. They in each transaction you have a transaction ID, an input, and you have at least one output. So in this example, we're taking 100,000 Satoshis and taking it from as an input to the transaction, and then you have an output 0 heading off to the input of the next transaction. Likewise, an output 1 heading off to the input of another transaction. And so the transaction 1, the output then goes off to transaction 2 as an input, which outputs then to something called an unspent transaction output. So that's a list of outputs in your wallet that have not been spent yet. You can, in that example, you can also branch off down to other transactions which include multiple inputs to sum them up to a single output and load it into the unspent transaction output list. So the wallet keeps a record of all unspent transaction outputs. Each output is tied to a transaction ID. Therefore, there are two categories of transaction outputs, spent and unspent. Transaction includes a cost to be awarded to a miner, and a higher transaction fee will mean that the transaction will be included into an earlier block by a miner as a higher priority. Miners create a block to be mined by incorporating transactions and then undertake a proof of work to prove that they have processed the block successfully. The proof of work is to take a hash of the block header and find a hash under the current target threshold. That's a difficulty which you can make more difficult by adding more zeros at the front of the target hash. And so the target hash becomes longer, it's harder to find, you end up with a more difficult solution. All of the pool of miners, the difficulty is scheduled so that every 2 weeks it's changed to make sure that the pool of processing power it takes on average 10 minutes of processing to solve the puzzle to find the hash. Once a miner has found the hash, they can pass around the peer-to-peer network to say, hey, I found a block, here's my proof of work, can you confirm that I found it? And eventually they branch off into different sections to see who, depending on a peer-to-peer network. So you'll end up with different heads of the blockchain, and eventually over time, more heads will be confirmed, and a head will win out as the most successful head of the transaction chain. So that will become the head of the blockchain, and at the same time, so it's not unusual for pools to have whole branches going off for multiple transactions and then being cut and having to go back to what the consensus has agreed is actually the real blockchain, and you have to go back. So a successful mined block is added to the blockchain and passed around the peer-to-peer network. And once a quorum appears in the peer-to-peer network, confirm the new block and have added it to the blockchain. Consensus is reached, and the block is officially part of the consensus blockchain. So here we've got an example of an output of a transaction being signed by a key, and this is how you spend a transaction. So in the transaction one, you have the transaction identifier, the output, a sequence number, the amount that is being to be transferred up at the top, and a public key script. So this is a script of a public key it's a public key pair that the wallet maintains for being able to send a transaction out to the network to send money to someone else. They append the transaction with a script that only the person with the wallet with the private key can use that output of that transaction. And that can be seen in the second picture, where Bob's computer has a private key, a full public key, a public key hash is sent to Alice's computer, which has a copy of the public key hash and can now verify that the public key hash is the address of where you're going to send the money. So the transaction one is created with the output, or the signature of Bob's public key pair, so that it can be verified that it's being sent to Bob's address. Hopefully I haven't confused it too much there. Okay, so next we've got, basically you've got the signature script, which is a signature of the transaction from Bob's private key to say this is my, I own this public key, so I can use it. So this is taking the transaction output from the transaction that Alice gave, and now this is Bob taking the output and verifying that he has the public key and passing it to further transactions that he wants to use and spend of those outputs. So Bob will create an unsigned transaction, sign the transaction before broadcasting it to the network. Bitcoin wallets have the functions built into them, managing private key, public keys, monitoring outputs, creating transactions, and signing transactions and broadcasting transactions. And that's what you can see in the full service wallet. You can create public key, private key pairs, distribute them, etc. So an example of the cryptography, it uses ECDSA curve, which it can be seen, which is SecP256K1, and that can be seen in the two diagrams. It's a curve that is evaluated over a prime field ZP. So over real numbers, it looks like the curve on the left, and over a field, over numbers 0 to 17, it looks like that. So now we have wallets, transactions, nodes, and miners. And a Bitcoin full node consists of a blockchain, a wallet, a peer-to-peer networking port, and a JSON RPC port. So now we've got everything that we need for a Bitcoin full node. Now we get to the honeypot. So I chose to write this honeypot in Golang. It's got secure protection against memory corruption. It uses the Bitcoin peer-to-peer network, uses 8333 for transferring data, and for JSON RPC, which is basically taking remote procedural commands as an API and saying I can control the full node. Usually it listens on 8332, but it's bound to localhost. So the honeypot, what we're doing is binding it to 8331, and then on the honeypot and the local host with the full node, and then opening up another connection to 8332 over the public internet. So we're basically saying, here's if you want to try to communicate to my Bitcoin full node, I've got a port on 8332, have a go. So the API documentation for Bitcoin, there's 98 API commands that you can use on a Bitcoin full node. Of that, 34 were evaluated to be considered dangerous to a honeypot. So that I'll go through some of them later. But basically, out of the 98 commands, first of all, if it's considered safe, then we can pass it through to the Bitcoin full node, let it do its job, and then pass it back to the attacker. If it's dangerous, then I've had to write a mimic, basically simulating something that would look like it's doing its job, but not actually damaging the honeypot in any way. So the aim was to make the deception as faultless as possible, to not give away that it's a honeypot, and that includes the use of fake transaction IDs and an extra layer of added and disconnected nodes. So a transaction ID is generated when you go to send money to create a transaction. The Bitcoin full node comes back with a transaction ID. To simulate that, I send off the request as if it was. Actually, I create a fake transaction ID. So I don't actually send it off to the Bitcoin full node because that'll actually send it off. I create a fake transaction ID out of a hash and make it look like it's what it's supposed to. They give it back to the attacker, and they've got a transaction ID that fits the rules, and then they can go and have a look at Blockchain Explorer and see what's going on, see if anyone's used it, is it real, etc., etc. The added and disconnected nodes. So in the peer-to-peer network for Bitcoin, you can, on the nodes layer, you can add nodes to the list of connected nodes that the honeypot the full node connects to. So what I did was I simulated a layer of for each IP address that connects to the honeypot. If they add a node or delete a node or create a banned node or clear the banned list, all of that is simulated just for that IP address. So they think that they're adding a node, and it appears in their list of all nodes connected if they communicate through the honeypot, but in reality, it's not actually connecting to the node. So it's a layer of subterfuge just to say, okay, that I'll show you that it kind of looks good, but if they're trying to connect a malicious node to my node, I'm not going to let them. So this is a process, a simple process map. So a request comes in to the honeypot. We check for whether it's a get HTTP get or a HTTP post. Check for authentication. It's using HTTP basic auth on the API, so no TLS or anything like that, just open HTTP API. And then once it comes in, we unmarshal the JSON and determine what the API command is. Is it what we would consider safe, and therefore can it be whitelisted? Or is it dangerous and we need to blacklist it? If it's a blacklist, then we simulate, mimic the Bitcoin Full Node response. And if it's a whitelist, we send to the Bitcoin Full Node and pass through, and both of those branches come back to the attacker. And so this is the communications path, what I was just describing. Attacker sends to the Bitcoin Honeypot. If it's safe, we pass it through to Bitcoin Full Node. If it's not safe, we don't send it through to the Bitcoin Full Node. And that's the blacklist equivalent. Okay, so I'm going to go through a couple of the API commands that were considered dangerous, and therefore we blacklisted them. And so there's a little description of what they do and why they would be dangerous. So add node, if we could let an attacker add a node, then it would signal to an attacker that if the honeypot is not connected to the network. So we've got to simulate that there is a node, that it looks like it is actually connected when it's not. Likewise, backup wallet, that saves the wallet to a local file on the computer. If the host is compromised, then the wallet could be stolen, so we don't let them do that. Clear band and disconnect node are associated with band lists and nodes, and so we simulate as what we were talking about before. The private keys, if you don't want to let an attacker dump the private key back to them, either returning it to a local file or sending it over the comms. So that would allow an attacker with the private key to sign a transaction separately to send that address somewhere else, send that funds out of the honeypot. Dump wallet is similar. Encrypt wallet is also similar. Like if you let an attacker encrypt the wallet, that removes the deceptor's use of the wallet. Other people can't use it. You lose access to the money. Raw transactions. So you can use a simple command like send to address, and that will send money to the address that all scripted to one level. Just send to address, it'll just go and send a request off. You can do it another way and do it step by step, which is a raw transaction. So you can create a raw transaction, sign a raw transaction, fund a raw transaction, etc. So we don't want to let them do anything like that. Generate is associated with mining, so you can tell if the node allowed mining, the attacker could tell the node to start mining and tell it where to submit all of the funds, the rewards of mining. So when a miner does win the lottery of solving a hash, they get given a certain amount of Bitcoin as a reward. So a generate would allow an attacker to use the honeypot to mine, and then could be the funds can be sent to somewhere wherever they want. So that's the same with generate to address. Get account lets them know what account, who owns it, that kind of thing. Get mining info, get peer info, all associated with nodes and peers. Import private key. That would mean that you'd be able to import your own private key and use the honeypot to send to sign transactions that you have access to. So you could. There's no plausible deniability, that you could basically take someone's private key, load it onto the honeypot, and tell it to do something, and then you're implicated in some way. So we didn't want to allow that. Import wallet lets them bring in their own wallet. List banned nodes, etc. Moving money around wallets was another one we didn't want to let them do. Sending, so send from allows you to send from a particular account. Send many, send to multiple Bitcoin addresses. Send the raw transaction. Send to address. So that's the simple. Here's an address. Fire and forget. Banning, set ban. Sign message, that would allow you to use the honeypot to sign a message and you could simulate that person signed something and therefore had control over the private key in order to do that. Sign message with private key, that's supplying your own private key and telling the node to sign, etc. Raw transaction stop. Now, that's a denial of service. So telling the Bitcoin full node to stop. Verifying chain, that's another denial of service. That basically says go back to block 0 and re-verify everything. And if it's taken you 2 weeks to download to the latest head of the blockchain, that knocks your node off for 2 weeks to verify. And wallet lock is removes the encryption key, locks from memory and locks the wallet, so other people would need the password. Another denial of service. So an example of a mimic. This is a send to address. So the parameter 1 is of the JSON request is the to address. Parameter 2 is the number of Bitcoins. Parameter 3 and 4, I believe, are optional. They're comments. And parameter 5 is an automatic fee for subtraction. And the output, the result is a transaction ID in hex in reverse byte order. That's just the way that Bitcoin API structures its addresses. So to mimic, what I've done is I've taken a string of all the parameters in the attacker's request, dropped the last character just for creating something different. Hash using SHA-256, encoded as hex, send it into reverse byte order, and send to the attacker as a transaction ID. Now, if they go to the blockchain explorer, they will not find this transaction anywhere because it's a fake transaction, or if it's unlikely, but it's possible that you end up hitting the exact same transaction ID as something someone else has used somewhere along the way. But it's a hash, so. All right, so this is I'm going to show you briefly what I've done from a demo perspective. So this is an example of a whitelist command. So first of all, start up Bitcoin D, the daemon for the full node, and then run the honeypot. So it's listening as a post server on port 8332. And then I'm using Postman as a post tool, which allows you to, that's the JSON. So in that, I'm sending it to localhost 8331, so that's to the full node itself. And I'm setting, give me the get blockchain info. And so that's given me the details. That's directly to the full node that I'm not exposing everything to. And so the head block, the block count, will show as the exact same number as me doing it. So what we would do is send it through the honeypot, and the honeypot will just pass that onto the full node. and you'll get the same result. And I think that that's what it's about to do. So it's on port 8332, which is the public internet listening port, and get blockchain info, and it'll respond with the same node IP block count. And now I'll show you an example of that continues for a little bit longer. And now I'll show you an example of a blacklisted. So start the Bitcoin daemon, start the honeypot. Move over to Postman. And so this is going to, this is the request to the full node. And I think it's get account. And the answer is null, is empty, because I didn't give my wallet a name on the full node. But in the honeypot version, I give it a person's name, and that's what this will show very quickly. So it sends to the honeypot, and it comes back with Simon Smith, our good friend. So that'll do for the demo. So for deployment, So for deployment, I basically picked a random cloud provider that's located in the USA. Because of the size of the blockchain, it's up around 180 gig at the moment. There you go, 184 gig. So I chose a dedicated server. I didn't want to deal with expanding storage and computing power and the potential rising costs of cloud versus a simple dedicated. And the requirements, so Bitcoin Core Full Node and Golang, and I gave it US $250. Well, that's what it is at the moment. I think it was up around 500 at the time that the attacker was playing, and it's been deployed since November 2017. So here's a brief timeline. November 2017, almost immediately, we're getting TCP SYN scans. So that's your census bots or your showdown or the criminals bots. They're bots just checking to see what's actually open on this port, on this IP. Then in February, I noticed web vulnerability scanners. So it was actually coming up the stack to HTTP, and they were making fully formed requests. So that's web vuln scan. They're all gets, no posts. So there wasn't any response. I think there was one post, and it responded, no, you need to actually use post. It responded unauthorized. So in March 2018, we had a manual request. It's a Bitcoin post request, and that responded unauthorized. So they're trying to do it without the username and password of HTTP basic auth. And then we start seeing something a bit more interesting in April. So the 9th of April, a web vulnerability scanner came in. The 10th of April, unauthorized Bitcoin post requests. And then later on, we started seeing they created a dictionary of usernames and passwords, and they were actually having a good red hot go at trying to break the authentication. So I gave it a fairly simple username and password, RPC user, RPC password, and it was accessible. So I can just imagine what they're thinking. I've got to get my hacker hat. All right, I'm in. So a hacker walks into a bank. What's the first thing they do? They check, okay, well, how much money have they got? So they've got, turns out they try to get balance, and they've got $250 US. All right, that's kind of cool. Send to address. Let's just get this money out. Okay. They get a transaction ID, but it's a fake one. It's the one that I gave them as a SHA-256 incorrect. So they go to Blockchain Explorer, and they have a look, and it's not there. What's going on? Something's not right. Okay, let's try again. So they look around. They try it about 30 times. Like they're literally trying to get balance, trying to send to ID. Okay, I've got an ID. Wait, this doesn't work. Get balance. Send to address. It was just they were clearly just not quite sure what's going on. So they eventually checked out the wallet a bit further, get addresses, get new addresses, set a transaction fee, send to address. Bam, fake transaction ID. What the hell? Not right. Something's not right. So they sleep on it. So now we're in May, so it's like a month later, and they do the same thing. It's like get balance, send to address. They get a fake transaction ID. What's going on? Okay, well let's try something else. Let's try dumping the private key. Oh wait, we responded with a bad method. That's not right. It's not meant to say bad method when you give them when you dump private key. Okay, let's try dump wallet. They responded with a null to look like it did it. So we decepted, but they still getting a bit sus. So they try sending 3 commands at once rather than just a single command. Now I didn't write it to deal with multiple commands at once. So I threw a parse error. Tried to do 3 JSON requests at once, couldn't deal with it. They realize it's a honeypot and they're never to be seen again. So out of that exchange, what did we learn? The first stage was you get hit with SYN scans and VOLD scans. The second stage would be to brute force the authentication. And the third stage is to try to send the money out as quickly as possible. So I was a bit disappointed. They didn't try any of the really cool simulated networks or ban lists or anything like that. Nothing. It was just purely send to address. So we also learned that the IP addresses varied. We had requests coming within seconds from 3 different IP addresses in the Netherlands, USA, and UK. So they're using some kind of botnet to provide the requests. It was quick to find, so almost immediately it was being hit by TCP SYN scans. The send to address was used. So I had a look at the address that they used to send it to. It did not appear to contain a history of other transactions or any other storage of value. And they were deceived until the end. They were there. They came back a month later and thought, what the hell? Let's fix this.
Are you trying to send all transactions just to the same wallet or to different wallets?
To the same address.
How could you track if there was the same individual or same group?
Only their pattern. So the IP addresses were mostly coming out of the Netherlands. I had a small analysis of the time, and it landed within 8-hour periods between 9 a.m. European time and 8 p.m. European time. So pretty much right in your Central Europe.
And using the same authentication.
Yeah, so within seconds of each other came from 3 different IP addresses. So that's my summary of some research that I did to have a look at what we can do for setting up a trap and putting it up and seeing if we can see anyone trying to steal money from me.
Is it still online now?
Yes.
Yeah, right. Have you tried linking it to Pastebin and see what happens?
That'll be. I haven't tried that. No, that's a good one. I think that they in their CRM or their log of this is an IP address and this is the history of this port. If someone's come through and gone right, that's we'll come back to that later, and that's what happened in May. And then later on, they're like, this is a honeypot. So from then on, like I disabled auth just to see what would happen because I wasn't getting any bytes, and that's just web vault scanners as part of programs, no manual human intervention. Yes.
I'm surprised at the number of attacks because I thought there'd be a lot more people trying to get in it. So
they were different. Some of them were trying, like over the months leading into it, but they weren't trying very hard. As soon as they hit the auth, they're like, it's too hard. It's not easy money. Got to try. It's too hard. So having the auth there made it look like it was a real full node, and it had real money in it. So anyone that wanted to, if they did get access past the auth, they could get the value, get the address of where it had come from and trace it to see that it had come officially. It's not a honeypot.
Any other questions?
Yeah.
Would you actually use this as a honeypot as a service?
It's possible to develop it a bit further. Put a better logging system on, send it to a elk stack, do some more analysis on it. At the moment, it's just a single IP. So part of the plans would be to build it as something bigger. And there's always the possibility, exactly, if there's interested parties out there that want to see, there's something that could be investigated.
One idea that we can do as well, we can like remove like authentication, put in the internet, start reporting like the wallets that bots come back and try to transfer the money, you know? So pick like a list of wallets and you can, I don't know, report to someone or at least like tracking which kind of wallets are used for criminal activities and this kind of stuff.
Yeah, that's a good suggestion. Yes.
How do you keep your private key safe, or how would you recommend to keep your private key safe?
No, it's because I've only been dealing with the honeypot. I would keep the wallet well protected. The wallet takes care of the private keys and manages them. So it's a DAT file that the wallet is that you need to well protect. Now that could include some of your storing it offline, storing it in hardware, in cold storage. As someone was talking about paper seeds. There's all sorts of things you can do for the really paranoid.
Any other questions? Thank you very much.